We ended the last video with this example. We had these conductive rails, and we were sliding a conductive bar back and forth, and that's an easy way for us to change the area and still maintain that conductive path for the electrons to take. So we still have a circuit as we change the area that the circuit encompasses. We used Lenz's law to figure out what direction the current flows in this circuit. We said the bar sliding to the right increases the area, which increases the amount of flux, and the magnetic field is pointing into the page. So we're increasing the flux into the page. A current is going to get set up to try to get it back to its original state of low flux. It's going to try to subtract from the magnetic flux caused by this external magnetic field. And it's going to go counterclockwise, so its own magnetic field comes out of the page and subtracts from this because it's trying to oppose the change. If the magnetic flux is increasing, it tries to subtract from it. If the magnetic flux is decreasing, it tries to add to it. So we got our current was flowing counterclockwise. So we came to that conclusion using Lenz's law. We looked at the change in flux and said that the induced current had to create its own magnetic field that opposed the change in flux that created it in the first place. Sometimes it's easier just to do it than to put it into words. We used Lenz's law and we got the induced current is counterclockwise. Now let's take a look at just forces. Just looking at the forces on the charged particles in the rod as it's moving in the magnetic field. I'm going to make my charge positive. We know that this conductive bar is filled with electrons that are free to move around, but let's pretend there's a positive charge in there that's free to move around because that's the direction of the current. And if this bar is moving to the right with some velocity, we've got a charged particle sitting in this conductor. What is a conductor? It's a material where the charges are free to move. So we've got a charged particle moving to the right. We have a magnetic field into the page. So this charged particle is going to feel a force toward the top of the page. As the charged particle moves in that direction, well, that's the direction of current. Current is the direction of positive charge flow through the circuit. So positive charges would feel a force up and move in the counterclockwise direction. So if we just look at the forces on the particles in the conductor, we get the same result. The induced current is in the counterclockwise direction. These two techniques only gave us the direction of the current flow. What if we wanted to quantify it? What if we wanted to know what is the induced EMF in this loop? And then we can look at the resistance in the loop and figure out the current. Well, there's a couple of things we can do. Let's take a look at this circuit using motional EMF. We saw in the last video that when you have a conductive bar moving in a magnetic field, the charges move, and this charge separation creates an induced EMF across the length of the conductive bar. Well, here we have a bar moving in a magnetic field, and so charges are going to move. The positive charges are going to end up at the top of that bar, the negatives at the bottom, and that's going to induce an EMF in the loop. And we saw in the last video what that is. And the result from the last video showed us the EMF induced across that conductive bar moving in a magnetic field is the magnetic field times the length of the bar times the speed of the bar, the velocity. And it's just as if we're hooking up a battery to our circuit with this EMF. There's also another way we can determine this value, and that's using Faraday's law. Faraday's law tells us the induced EMF is proportional to the rate of change of the flux. So let's take a look at that. Of course, all we care about here is the magnitude. We're just trying to quantify the value of this induced EMF. The direction we got from Lenz's law. Because we just have one turn in this circuit, n is equal to 1. And the flux is the integral of B dot dA. So when I evaluate this, this is the order I do it. I put in the integral of B dot dA for my flux, and I keep the time derivative separate from that, one thing at a time here. Is B constant over my area? If it is, then this is an easy integral to do. It just becomes B times the integral of dA, which is the area, right? If B is constant, it comes out of the integral. And in this case, B is constant everywhere. It's uniform magnetic field. So if I measure the magnetic field at this little location here, I get the same value as if I measure it over here, same value over here, same value over here. It's a uniform magnetic field. So this integral just becomes B times the integral of dA, which is the area. Now I ask myself, what's changing in time? Is the magnetic field changing in time? No, it's constant in time also. It comes out. So now I know the area of my loop is changing in time. Well, what is the area of the loop? The area of the loop is this length multiplied by this other distance here. I'll call that W, length and width. The area is equal to L times W. Let's plug that in. And then I ask myself, what's changing in time? Is the length changing in time? No, that can come out. The width is changing in time. The width of my loop is changing in time. Well, what is dW dt? The rate of change of the width with respect to time. That's the velocity of my bar. So my EMF is the magnetic field multiplied by the length of the bar, multiplied by the velocity of the bar. That's exactly what I got using motional EMF. There's one more way to think about this. A lot of people say Lenz's law is really just conservation of energy law. Because what would happen? Let's take a look at our circuit and let's just pretend the current goes in one direction and then let's pretend it goes in the other direction. We don't know which direction it goes. Let's just draw the circuit. So there's our circuit. And first we'll pretend the current is clockwise. And then we'll pretend that it's counterclockwise, and we'll see if one of these runs into problems, one of these assumptions. Okay, so we'll look at the situation on the left first. Current, we'll pretend that when we move this bar, the bar has to be moving. The bar was moving, what direction was it moving? To the right. So if the bar is moving to the right with some speed v, and if the current started running in the clockwise direction, let's pretend we don't know which one. We're just going to make a hypothesis here that it goes clockwise. So if the current is in this direction, what direction is the force on the current in that bar? We have a current going towards the bottom of the page in the bar, and the bar is sitting in a magnetic field. Well, I cross B gives us a force in this direction. So what does that tell us? We give this bar a little push to the right, the area starts to increase. If current gets induced in that direction, in the clockwise direction, it will feel a force to the right that causes the bar to move even more, which would cause more current to flow, which would cause a bigger force, which would cause the bar to move even more. We'd have free energy. All we do is give it a little push, and then it takes over from there and just gives us energy. As long as there's still rails to ride on, it gives us free energy. Well, we know that can't happen, right? We know we're not going to get free energy. If we want to get energy out, we've got to put energy in. We know that's a law of physics, right? Conservation of energy. So this would violate our law of conservation of energy. Now let's take a look at the situation on the right, which is what we know actually happens. We've gone through it 3 or 4 different ways and found that the current goes in the counterclockwise direction. So let's take a look at this. We give this bar a little push to the right. The area increases. Current begins to flow in the counterclockwise direction. And now we have a current moving in a bar in a magnetic field. It feels a force. In what direction is that force? To the left. So we push the bar to the right, current starts to flow, and a force is in the opposite direction. So if we want to keep the current flowing, we have to push against this force and do extra work to keep the bar moving. That makes sense. That's what we know about energy conservation, right? If we want to get electrical energy out, we have to put mechanical energy in. We have to do some work. So from a conservation of energy standpoint, this is the one that makes sense, and that's what Lenz's law tells us. So a lot of people just say Lenz's law really is just conservation of energy.